everyone, welcome into lecture number 2 on calculus with vector functions. In this lecture we are going to define derivatives and integrals of vector functions. Recall that in the last lecture we defined what we meant by a vector function and its corresponding space curve. So let's start off first with the definition of derivative. So we've got derivatives here. Suppose that we have a vector function. So suppose r equals r of t is a vector function. And let's suppose, for the sake of this one, I'm going to write this like this. Remember, the vector function takes in a real number and gives back a vector in Vn. I'm going to sketch a picture in a moment, and I'm going to sketch it in 3 dimensions. But remember, we could be in either 2 or 3 dimensions or more dimensions. But physically, we're going to do most of our problems in 2 and 3 dimensions in this course. All right. Now we want to talk about the derivative of this function. So like I said, let me sketch a picture of this. The idea is going to be very similar, at least geometrically, to the derivative of just a regular function in Calc 1. So here's our x, y, z coordinate axes. And remember how this vector function works. So it takes in a value over here, call it t, and the vector function is going to assign, for every value of t, it's going to assign a vector over here in 3-dimensional space. So I'm going to say this is r of t0. Call this one t0. And then let's suppose, say this is t1 up here. So maybe this one does something like this, r of t1. All right, and so what we would like to do is define the derivative of the vector function, and then in between there's the vector function can take in all the different values in between here. But I wanted these two right here because here's the idea. Remember, this traces out a curve, right? So we get our space curve, C, which is in some sense the graph of R. And the idea now is we want to try to understand what happens when we take the derivative of the vector function. So I'm going to write down the definition, the limit definition of derivative of the vector function, and then we can compare with the picture here. So here's our definition of the derivative. So it's going to be dr by dt. It's going to be defined to be the limit as h approaches 0 of the difference quotient. So it's going to be r of t plus h minus r of t, all divided by h. So this is exactly what you would expect, right? This is if you drop the vectorness of this function or of this definition, then this looks just like the definition, the limit definition of derivative from Calculus 1. All right. Another way to write this is as follows. I mean, this one's fine. I was just going to replace the h with a delta t, but we'll just do that in the picture up here. So here's the idea. As h represents, like I was just about to say, represents the distance between these two. So let's say we're taking the derivative at t naught. Then as h approaches 0, this point's going to become much closer to this point. And so we're going to have the limit of the difference of these vectors, right? So the difference of the vectors, as we remember from Calc 2, is the vector that connects the tip to tip of these vectors here. All right, and so the difference of those vectors is going to determine the direction, and then we divide by this magnitude h, which is a very small change, right? So it's actually going to make sure that this stretches out a little bit. But the idea is, after all of this, what we end up with is the derivative. These vectors kind of, these look like kind of secant lines from Calculus 1. And then as h approaches 0, then t1 will approach t, right? T naught. And so what we end up with is a vector that is tangent, to the curve up here. And so this one is the derivative of r at t naught, okay? The notation that I use for derivative is r dot. So r dot. So this is the notation that we use here. So this can be written as r dot of t, or it can be written as r prime, if you want, of t. The dot is used in physics because that notation was initially used by Newton. When Newton invented calculus back in the 1600s, he used a dot to denote a derivative instead of a prime. And he actually made a whole mess of it, and he would stack the dots up really high, and people couldn't understand exactly, you know, I mean, they could understand, but it was a little bit messy. So the dots have been lost in many places of mathematics, of calculus, but in physics especially, and in this kind of calculus, we still use the dot to denote the derivative of a vector function with respect to t, okay? So here's the idea. The derivative is just the difference quotient, just like we would have done before. Let's investigate something here. So let's suppose that we are in 3 dimensions. So suppose our vector function is mapping our real numbers to 3-dimensional vectors. All right, then we can say, right, that our vector function can be written component-wise, just as we talked about in lecture 1, as the component-wise vector function, right, where the individual components are regular Calc 1 functions, x of t, y of t, z of t. So these are all functions of t. This is very similar to the parametric definitions from Calculus 2, right? So it's very similar. But now let's see what happens when we take the limit of these. And actually, what we should do for this one is write this in the other notation, that we have our x of t times I plus our y of t times j plus our z of t times the vector k, unit vectors. All right, and then let's take the derivative. So in this case, dr dt is going to be equal to, just like this, right, the limit as h approaches 0, r of t plus h minus r of t, all divided by h. And then we can plug in these definitions, or even we could even do this one. It doesn't matter. Let's go with this one though, right here. So this then becomes the limit as h approaches 0 of, upstairs we are going to have all of this with t plus h instead of t. So we're going to have x of t plus h times I plus y of t plus h times j plus z of t plus h times k minus parentheses, right, x of t times I plus y of t times j plus z of t times k. I've got, I overdid it with the arrows, right? So x, y, z are just functions. They're not vector functions, so they don't need hats. And then we have all this, all divided by h. And so this can now be distributed out, right? So we notice that we have this term and this term both have i's. This term and this term both have j's. And this term both have k's. And so what we can do is break this up, or at least group it. Let's say we can group this, right? So that we have the limit as h approaches 0 of, and then I'm gonna group this up and break them up by blue, green, orange, and then each one's gonna get their own h here. So this one's gonna be x of t plus h minus x of t all over h, and that's all times I, right? Plus, then we're gonna have y of t plus h minus y of t all over h times j, those are both times j, plus, this is now going to be z of t plus h minus z of t, right, all over h times k. And then we know from calculus that our limit can now distribute, right? Our limit can distribute. And so this is going to be then the limit as h approaches 0. Put this in parentheses. X of t plus h minus x of t all over h. That's all times I. I is a constant vector here, so that doesn't, the limit is not concerned with that. The limit's only concerned with the h's, right? And so then it's going to go to the next one. So we have another limit here. H approaches 0. Y of t plus h minus y of t all over h. This is times j. And then finally, we have the limit as h approaches 0, z of t plus h minus z of t all over h times k. Oh boy, hopefully we can see that. And then look what all of these are though. So these three terms are just the Calc 1 derivatives, the regular derivatives of the functions x, y, and z, the component functions, right? So this all comes down to, we can just take dx by dt times I plus dy by dt times j plus dz by dt times k. All right, and so what we end up with then is a theorem. So THM stands for theorem here. And we'll say it this way. The derivative, we've basically just proved it, right? The derivative of a vector function r of t equals x of t, y of t, z of t is given by r dot of t, right, equals, and then we can use the dot to denote the derivatives of these since they're with respect to the parameter t. So x dot of t, y dot of t, z dot of t. So component-wise derivatives, and then we just have to say anything that's defined by a limit, right? It's possible that it could possibly not exist. So we just have to say provided the derivatives exist. Okay, so this is a long-winded way of saying, right, that the derivative is defined by this limit, but computationally we know how to take derivatives of these functions without having to use the limit definition in Calc 1 and Calc 2, so we can just apply the derivative component by component. The derivative is component-wise. That's what we can say. That's a way to interpret this theorem, right? So the other thing, the next thing I should say, is how do we interpret the derivative? We're going to do examples in a minute, but how do we interpret the derivative with respect to like physics, so physical interpretation? So what's the physical interpretation of the derivative? So here's how we are going to think of this. So let's suppose that a particle is moving through space. I'm going to do this in three-dimensional space again, but this applies to two-dimensional space as well. Let's suppose a particle is moving through space with position function r of t. So r equals r of t. So this means that at any time t, the vector function points out where the particle is, right? And so we'll just draw the kind of very similar sketch to what we had in the previous one. Here's our x, our y, our z. I'm going to draw the curve first. All right, so this is a space curve given by the graph r of t. All right, and so let's suppose that at some time t, our particle is right here, and our particle then is picked out by this vector, right? It's described by this vector. So r of t gives us the position of the particle. The terminal point of the vector is the position of the particle in space. All right? Then the derivative of this position function, derivative of position is velocity, right? So the derivative is actually the velocity of the particle physically. And so sometimes that's called the velocity vector. But let's write this all down. So the derivative of r at time t is the velocity of the particle. At time t. All right, so for example, if this particle is moving this way, so if it's going this way around the curve, then its velocity vector would be tangent to the curve, and the length of the vector, so this is v of t, but it's also, so v for velocity, but that's r dot, right? That's the derivative of r dot of t. And the length of this vector, so let me change the color of this so that we can see it better. The length of this vector is the speed of the particle. All right? So the length of v, which is also confusingly written as v of t without a hat on it. Okay, so in your ebook, this is going to be a bold-faced v. We can't do bold with our pencil, so this one gets a hat because it's a velocity vector. Just regular v is the length of this, which is the speed, right? That's the speed of the particle. So this is the speed. All right. Now, as the particle could many different particles could travel along this curve at different speeds, right? So the direction of the velocity vector is going to be the same at every point for every particle that travels around this, but the length of those velocity vectors is going to change, and that's going to be the speed. All right, the length of the velocity vector is going to be what changes, but every particle that travels around this curve is going to have the same. It's going to have the same directions of its derivative at every point. So that gives us an idea that maybe the direction of the velocity, right? The direction of the velocity is somehow inherent to the curve. It's a property of the curve because every particle that travels on this curve, along this curve, is going to have the same direction vector, right? At every point. And so that is something very important. That's called the unit tangent vector. So the unit tangent vector, at each point this is a unit vector that points in the direction of the velocity. We have to say something else before I write down a formula for it. So the way that I've defined this brings to light one possible problem, right? The possible problem is that the velocity could be zero at a point. What if a particle decides to stop and take a break? Then its velocity is zero, right? So we have to define something called a smooth vector function. So here's a definition, and then we'll talk about we'll write down a formula for this unit tangent vector. But in terms of the picture, if this is the r dot, let's say this is longer than a unit vector, right? Then the unit tangent vector, provided we can compute it, is going to just be, it's going to be a vector of length 1, right? That's in the same exact direction as our velocity vector. So here's the first thing we need to do, though. We need to define something. So we need to say this. A vector function R is smooth if its derivative r dot exists at every point. So we can take the derivative at every point, and, okay, this is the key, and r dot of t is not equal to the zero vector at any point. So I'm going to say at all t in its domain. And this is to make sure that our particle doesn't stop and take a break, right? If our particle stops and takes a break, what we have to do is chop our curve into multiple pieces everywhere that we stopped and took a break, right? And just treat the portions of the curve that have a derivative not equal to zero, treat them separately. All right, so this is very important, so smooth. All right, now we'll write our definition of our unit tangent vector, all right? So for this one, let's say, suppose R is a smooth vector function and so that encapsulates all of this, right? We can take the derivative, we can take this derivative right here, and we know that it's not going to be zero. So just by saying this word smooth, we have encoded both of those pieces of information, right? So suppose R is a smooth vector function. The unit tangent vector, and this is actually called a tangent vector field, but we're not going to worry about field yet. We'll talk about that later in the semester. But the unit tangent vector field is defined to be this. capital T of t. That's just the same notation I used up here, but we still don't know how it's defined, right? Well, it's got to be a vector in the same direction as r dot, but we want it to be a unit vector. So we're going to take our velocity and divide out our speed. Okay, if you take your velocity vector and you divide out your speed, then you have a unit vector in the direction of velocity. So the definition down here is going to be that this is r dot of t divided by the length of r dot of t. Velocity divided by speed. Okay, and that just gives us the direction of our velocity. All right, and so this is the definition. Again, we made the assumption that it's smooth, so smooth means that we can divide. Number one, we can take the derivative, and number two, we can divide by the length without having to worry about it being zero. All right, so that's the unit tangent vector. All right, let's do an example now. This will be item 3. Here's a vector function. So r of t equal to, how about this? Arctangent of t, 2e to the 2t, and 8t e to the t. So this is a vector function in R3, three-dimensional space. And what I would like us to do here is find all three of the following. So find r of 0, r dot of 0, and t of 0. So what does that mean? That means find the... I have not written exactly what I want you to find. R of 0 is fine. I also want one more thing then. I mean, we need t of 0. This is good enough. This is fine, because we'll have to do everything that I want us to do on this one, just by the way I've defined it. But yeah, the idea here is that we want to plug in 0. So this 0 right here is the t value, right? So I'll say at t equals 0. And that encompasses all this. So we want r dot, and t. All right, take a minute to work on this yourselves, and then we'll come back and finish it off together. Okay, now that you've had a chance to work on this yourselves, let's try to work on it. Let's try to write down the answer together. So a couple of things. The first thing that we're asked to do is just plug in 0 to this function, right? So r of 0, that we do by just putting in zeros, right? So this is going to be arctan of 0, 2e to the 0, and then 8 times 0, e to the 0. So arctan of 0 is 0. 2 times e to the 0 is 2, and 8 times 0 is 0. So there's r of 0. It's the vector 0, 2, 0. If we think of this as a particle, then this is the position of our particle at time t equals 0. All right, the next two things we want to find involve r dot. They involve the derivative. Well, we have to take the derivative before we plug in 0, right? So r dot of t needs to be computed before we can plug in 0. So r dot of t is just, we'll just go in order. The derivative of arctangent is 1 over 1 plus t squared. The derivative of this is going to be a chain rule, so this will be 4e to the 2t. And then this one is a product rule, right? So it's 8e to the t plus 8t e to the t. So there's our derivative. And now we can plug in 0 to this. So r dot of 0 is going to be 1 over 1 plus 0. So that's 1. 4e to the 0, that's 4. 8e to the 0, that's 8 plus 0. So this is 8. Okay, so there's our r dot at 0. This is our tangent vector. So this is the velocity vector, right? The tangent, when I said tangent vector, I didn't say unit, right? This is the velocity vector. It is tangent to the curve, but its length is probably not 1. And just looking at it, it's not going to be 1, right? The length of this is more than 1. So that this is the velocity vector. And to find the unit tangent vector, we have to know the length of this, right? And since we only care about that one at t equals 0, we can just find the length of this as it is. We don't have to worry about computing the length of the vector function here. We don't need the, in other words, we don't need the speed function, right? But the length of this vector is going to be the square root of the sum of the squares. So this is going to be given by this, right? Which is the square root of 81. Right? That's 81, so that's obviously 9. So there is our speed, right? The speed of this particle at this point is 9. And now we're ready to make our tangent our unit tangent vector. So this is going to be r dot of 0 over length of r dot of 0. So it's the vector function 1, 4, 8 divided by 9. Remember how you divide a vector by a number? It's got to be component by component, right? So the unit tangent vector at this point is the vector 1/9, 4/9, and 8/9 in the third component. This is in the same direction as the velocity, but its length is 1. All right, so that's the unit tangent vector field. Okay, so now that we've computed this, it's pretty straightforward, right? Let's talk about some differentiation rules. And this is going to be actually a theorem. We'll prove one of them. But these are differentiation rules. All right. Here's what we have. We need to first lay the groundwork. So let's suppose that u and v, suppose these are vector functions. So I'm going to say differentiable as opposed to smooth because these could have derivative equal to 0. But differentiable vector functions. And we don't care what dimension the vector functions are in. So they're both going to map r, right, to vn. And it doesn't matter what n is as long as it's the same for both of them. So u and v have the same n. There will be a time when we care about this in just a moment, right? Which we'll write it down when we need it, right? And then let's also let f be a regular function, just a real valued function. So a real valued differentiable function. In other words, not a vector function, just a regular function. And then let's let c be a scalar. Scalar is just the word for number when we're talking in vector language, right? A real number in this case, but not a function, just a fixed real number. Okay, then here are our rules. The first one says the derivative with respect to t of u of t plus or minus v of t. Sum or difference rules. What do you think is going to happen here? Well, the derivative is going to be linear, right? It's going to distribute over these two. So I'm going to write the left-hand side in this notation, and the right-hand side I'll use my favored dot notation. By the way, if you guys hate the dot, you can use the prime notation if you want. Just be careful. But there you go. So the derivative, this one says take the sum or difference first, and then take the derivative. And this side says take the derivatives first, and then take the sum or difference. And this rule says that those are equal. The order doesn't matter for those. All right. Similarly, derivatives being linear means that they should, we should be able to factor out constants, right? Scalar multiples. And it turns out that we can. So this becomes c times u dot of t. So this one says, again, multiply by the constant or by the scalar first, then take the derivative. This one says take the derivative first and then multiply by the scalar. And those are going to be the same. All right. So those are pretty straightforward. The next one that we have a few actually product rules, okay? More than one product rule, and we'll see why. But let's start with this one. Let's suppose that instead of a scalar out front, we have a function out front. So f of t times u of t. In some sense, this is like a scalar because for every value of t, it's just a number, right? And it's not a vector. It's just a constant, a real number. But for every value of t, it could be different, so it's not constant, right? It's a real number, though. So it should be similar to this, but the problem is that if this is changing, then you can't take it out of the derivative, right? So this has to obey a product rule. And the product rule is going to be the usual product rule, especially if we use our dot notation. So f dot of t, the derivative hits the first, leaves the second alone, plus then it's going to leave the first alone and take the dot derivative of the vector function over here. All right, these are both vector functions. These can be added together. This makes perfect sense. Now, usually, by the way, this is a theorem because we should be verifying these, right? So there are homework problems and recommended exercises that you verify all of these. We're going to verify one of them together in a few moments, but actually, this is the one we're going to verify. This next one I'm writing down. This one says that the derivative of u of t dotted with the second vector function v of t. We've got our second vector function. This is one way to multiply vector functions together, right? A vector function times another. As long as they have the same dimension, then we can take their dot product, right? And this then becomes a regular Calc 1 function after you've taken the dot product. So this says take the dot product first, get a regular function, take its derivative, right? And so the rule is then that this is going to be the same as first taking the derivative of this one and dot producting it with the second one, and then leaving the first one alone, dot producting it with the dot derivative of the second one. All right, so the product rule applies to the dot product of two vector functions. And again, this will be a regular function, add them up, you get a regular function. So at least the kinds of objects that they are the same, right? All right, if we can do this with regular scalar or function multiplication and with the dot product, we imagine we can do it with the cross product as well. The cross product requires that our vector functions are in three-dimensional space though, right? So I'll write this out. U of t cross product with v of t. But the only way that this makes sense for the cross product is if these are three-dimensional vector functions, right? So if it's v3. So for I'll just write it on the margin over here. So these ones are for v3 only, right? So, but the rule's exactly the same. Now with the first two, it doesn't matter if I switch the order of these, nothing's going to change, right? But the order of these does matter, and so the derivative has to hit the first one first and then hit the second one second, okay? The order matters for the cross product. That's something we should always remember. The order matters for the cross product. So this one says we take u dot of t, cross it with v of t, right? And then add to that u of t crossed with v dot of t. But this one holds just like the others. All right, so three product rules. Like I said, we're going to prove this one in a second, this middle one, because we need it for something else. So, but we also have a chain rule, okay? So the chain rule is the last one. And this one says this time we want to take the derivative of u of f of t. All right, so f of t is going to take our real number, make it a different real number, and then plug that into your parameter for u. All right, and this works exactly as you would expect it to. And that is that this becomes f dot of t times u dot of f of t. The usual chain rule. All right, so this is our chain rule. Okay, let's now prove, let's prove number 4. So this is our product rule for our dot product. Let's do it. I'm going to do this one with just a vector function in 2 dimensions, with vector functions in 2 dimensions, and I think you'll see how it expands, but you can do it for 3 dimensions. So let's suppose that u and v are vector functions from r to v2. Okay, so then we can say that our u of t is equal to, let's say, x of t, y of t. We'll let this one be the kind of usual one. And then v of t, say this one is made up of f of t and g of t. Has to be different, right? So if I want to call the coordinates x and y, maybe I should call these all letters that are different from x and y. But if these are functions, then these have to be potentially different functions. And now we just want to check both sides of this equation, right? So on one hand, we have, this one said, the left-hand side says to take the dot product first, right? So u of t, dot product with v of t, is equal to the product x of t times f of t plus the product of y of t times g of t. All right, and then take the derivative. So the derivative of this is, by definition, the derivative of this product, right? All right, and then when the derivative hits this, these are regular products, Calc 1 style products, so the product rule has to apply to each of these, right? So let's see. Let's see what happens here, right? So this is going to be derivative of the first, so that's x dot. I'm going to drop the of t. We know the of t is here, right? So everything here is a function of t. But we have x dot times f plus x times f dot, right? Plus, then here we're going to have y dot times g plus y times g dot. And so that's product rule of each of these. As this derivative hits each of these, they each get a product rule. So we have these four terms, and now we can just kind of regroup these. So we notice that these two have dots in the first one, and these two have dots in the second one, right? So let's see if we can group this together. So this one I'm going to write as x dot f plus, I'm going to just rearrange, just swap the middle two. All right, just swap these middle two terms. And look what happens. We get then y dot g plus, this one's going to then be x f dot plus y g dot. And now we can group these two, and notice that these ones look like a dot product. So this one looks like the dot product of x dot, y dot, dotted with f, g. And this one looks like x, y, dot product with f dot, g dot. Okay? X, y, that's u. So x dot, y dot, that's u dot, right? So now we can see exactly how this is going to work. This one is u dot, dot product with, this one's just v. This one is just u, dot product with, this one is v dot, right? There's v, so v dot is the component-wise derivatives. V dot, and that's exactly what we wanted to prove, right? Because now we've shown that on one hand we had this, right? And then on the other hand we got to the, this is a weird way to say this because we just got to the other hand, which is this, and in between we have equals all the way. Okay, so this is true for three-dimensional space as well, and really n-dimensional space. You can see that to do this with vectors that have more components, you just end up with more terms that you have to regroup, but it's going to be exactly the same. Okay, so we're going to call that a proof in general. That's the proof for 2 dimensions, but we'll believe that we can extend it to more dimensions. All right, so here's an interesting theorem. And this is one that we're going to use a lot moving forward. But let's say the following. Suppose that we have a vector function with the following property. So let's suppose that our vector function obeys the following property. Let me write more words here. So suppose R is a vector function that obeys the property that the length of R of t is equal to a constant for all t in the domain. So in other words, this particle, the length of the position function is constant. So for all t in the domain. All right, then the conclusion is then R is orthogonal to R dot, to its velocity vector for all t. All right, so let's prove it. So here's our proof. Again, I'm just going to rewrite the assumption here, but I'm not going to write all the words. All right, so suppose that the length of R of t is equal to c. So c is a constant here. Then what does this mean? This means then that the length squared of this vector is equal to c squared, which is also a constant. So this, if this is a constant, the square both sides is still a constant, right? Still a constant. And now recall that the length squared of any vector, including a vector function, right? That the length of a vector squared is equal to that vector, oh boy, there's a dot, but it's not there. So it's to the vector dotted with itself. right? So the length, the magnitude squared of any vector is equal to that vector dotted with itself. It's the magnitude squared. So look what we have now, right? Just equate these things. Thus we have r of t dotted with r of t is equal to this constant squared. Now we can apply the derivative. So now we differentiate. All right, and we get d by dt of, this is like an implicit derivative, right? R of t dot product with r of t, that's got to equal the derivative with respect to t of this constant on the other side. Well, on the left-hand side, this is a dot product of two functions. It's got to obey this rule that we just proved, right? It's got to obey this rule, this derivative rule. And so on this side, this is going to be r dot dotted with r plus r dotted with r dot, right? Just apply the product rule. It doesn't matter that these are the same function. You have to still apply the product rule, right? And on this side, the derivative of a constant is just 0. All right. Now, these two, the order, the dot product commutes, right? So we can change the order of these two and write the following. If they change the order, then these are the same, and we can just write that this is 2 r dotted with r dot equals 0. But that means, therefore, divide by 2, right, that this is true. R dotted with r dot is equal to 0. Remember that this is the definition of orthogonal. So this symbol right here means orthogonal, and the definition of two vectors being orthogonal is that their dot product is 0, right? And so we conclude then, therefore, in this scenario, then r is orthogonal to r dot. And then I drop the t here because the t, it's true for all t, right? This is true for all t in the domain of R. All right, so there's a theorem. Whenever we finish proving anything in this class, we're going to put a little box to let the reader know that we're done, and then maybe a smile, just to celebrate, right? To celebrate our hard work. Okay, so we're going to use these derivatives and these ideas of derivatives extensively moving forward. But let's now shift gears to definite integrals. And we don't need to say a whole lot about these because they are going to work exactly like the derivatives in the sense that they are going to be component by component, okay? So component-wise. So let's write this out, though. Definite integrals also can be applied component-wise. All right, so the reason for this is because they are defined by a limit. And so that's ultimately, if we scroll back up to our kind of derivation up here, it was before this, right? Here, our derivation. The reason that the derivative was able to be done component by component is because we could break up the limits component by component, right? And so the derivation of the Riemann sum definition of the definite integral is going to be exactly the same, right? So I'm not going to work it out, but I'm going to write a couple words here. And we'll call this a recommended exercise. So write out the Riemann sum definition of definite integral for, let's just do this vector function from a to b of a vector function that looks like, say, x of t I plus y without a hat, y of t j plus z of t k dt. All right, so there's an integral. So this is, by the way, the integral from a to b of r of t dt. If our vector function r is x I plus yj plus zk, right? Write out the Riemann sum definition for this and show that this must be true, right? So here's the key. This is how we're going to compute these, right? Show that this is then equal to, this integral is going to distribute to each term, okay? So it's going to be integral from a to b x of t dt all times I plus integral from a to b y of t dt times j plus integral from a to b z of t dt times k. All right, and like I said, this is what we're going to actually use to compute. So we wrote out all the details, all right? All the details were worked out for the derivatives and how the limits work for derivatives. You can't just assume that the same is true for integrals, but the derivation and the work is pretty much exactly the same, except that it's for integrals. There's still a limit, right? Integrals are defined by limits just like derivatives are. It's just a different limit. But if you guys work out all of those definitions, if you work that out, then you'll believe this, right? But let's use this though. So this is the idea. We can work out our definite integrals component by component, just like we do for our derivatives. And we believe the fundamental theorem of calculus as well, right? So if we can do the derivatives component by component, then we should be able to do integrals as well. And it turns out we can. All right. So if we believe this, then let's actually compute an example just to refresh on our integrals a little bit. So let's compute the integral from 0 to 1 of the vector function that looks like this. 1 over 1 plus t, 1 over 1 plus t squared, and t over 1 plus t squared. And this is all with respect to t. All right, so take a moment, work this one out yourself, and then when you come back, we'll do it together. All right, now that you've had a chance to work this one out yourself, let's write it out quickly together. By our definition up here, or in the yellow box, it's not really our definition, but we kind of skip to this step, right? This is how we're going to compute. Our computational definition, we'll call it. This is going to be the vector of component-wise integrals, definite integrals. So it's going to be the integral from 0 to 1 of this function, comma, the integral from 0 to 1 of this function, right, comma, the integral from 0 to 1 of this function, t over 1 plus t squared dt. So in reality, we just have to do 3 of these Calc 1 or maybe Calc 2 integrals individually and then put them all together into this vector function, right? So I'm going to try to do it all as a vector as we go, but we could actually, I'm not, you know what? It's probably better if we, just for the sake of, because this is the first time, if we take these all out and do them individually, right? So let's do this one first. I'll just do this. So the first integral, 0 to 1, 1 over 1 plus t dt. This is a natural log of 1 plus t, evaluated from 0 to 1. So this is going to be the log of 2 minus the log of 1, which is just natural log 2. Okay? We should be very adept at integrals at this point. But if you need to brush up, pause, you go brush up, and then you come back, right? So the second one, integral from 0 to 1, 1 over 1 plus t squared dt. The antiderivative of 1 over 1 plus t squared is the arctangent function. So this is arctan of t from 0 to 1. So this is going to be arctan of 1 minus arctan of 0. Arctangent of 1 is pi over 4. And arctangent of 0 is 0. So this entry is pi over 4. Okay? And then finally, we've got this one. And this one's going to be integral from 0 to 1, t over 1 plus t squared dt. This one, we need to do a little manipulating to get this to be a u sub, right? So then if this is u, its derivative is 2t dt. So this becomes a natural log. And we end up with then 1/2 natural log of 1 plus t squared from 0 to 1. So this is 1/2 natural log of 2 minus 1/2 natural log of 1. Natural log of 1 is still 0, so that's gone, right? And we just have 1/2 natural log of 2. All right, so that means that at the end of the day, our integral, right, is the vector made up of these components, and you have to make sure they're in order, right? So the integral, the definite integral of this vector function is the vector natural log 2 pi over 4, and then 1/2 natural log 2, and that'll do it, right? Okay, I've got one more problem for us to do with integrals here, and in the next lecture we're going to really get into the geometry of these space curves and how we can really learn a lot about the space curves from the vector function that parameterizes it. But our last one for this lecture, our last item for this lecture, is the following. Let's suppose that a particle is moving along a space curve with position function given by the following. So r of t is equal to t times I plus e to the t times j plus t e to the t times k. All right. And here's the question. If the initial position of the particle so if the initial position of the particle is r of 0, so I need to write this a little bit better, but if this is r of 0 equals the vector, so location 1, 1, 1, then can we find, sorry, I have totally messed this up. So this should not be the position function, this should be the velocity function. So the particle's moving along a space curve with velocity function r dot equal to this. All right. If the initial position of the particle is 1, 1, 1, then the question is to find the position function. So can we find a formula, a vector function for the position function? Remember, that's just r of t itself, right? Okay, so take a minute to try this one, and then we'll come back and finish up this lecture. All right, now that you've had a chance to work on this one, hopefully you did the corrected version here. What do we have to do? Well, number one, we have to find the antiderivative of this. So we have to take the integral, and in this case it's going to be an indefinite integral because we don't have any bounds, right? But we can still do that one component by component, and then we just need to find the unknown constants where you need to plug in this initial data. And just like we did on the previous one, we can do this one term by term, right? So we can do this term with this data, we can do this term with this data, and we can do this third term with this data. All right, and so let's start with the first component. So we need to first integrate, right? So our x component is going to be equal to the integral of t dt. So that's obviously going to be 1/2 t squared plus c, call it c1, all right? And we know that x of 0 has to be equal to 1. That's our initial condition. And so this tells us then, right, that x of 0 is equal to just c1, which is also equal to 1, and so there we go. And so our x of t is equal to 1/2 t squared plus 1. All right, so basic, same idea as we would have done in Calc 1 and Calc 2, right? Take the antiderivative, find the antiderivative with the unknown constant, and then use this extra information, this initial data, to solve for that c. In this case, I called it c1. All right, let's go to the next one. So the next term is what I've labeled as green. Right? So this one, we need our y term. So our y term is going to be antiderivative of e to the t dt. So that's just e to the t plus c2. The initial condition for this one's also that it equals 1, right? But y of 0 is e to the 0 plus c2, which is 1 plus c2. E to the 0 is 1. This whole thing's supposed to equal 1. So guess what? Solve this. This tells you that c2 is equal to 0. And so our y of t is just equal to e to the t. All right. And then finally we go to the third one. The one we've labeled as blue, right? So this one, z, is equal to antiderivative of t e to the t dt. This one is integration by parts. All right, so this one's going to be integration by parts. This is going to be our u, and this is going to be our dv. Right, and remember the integration by parts formula says that this is going to be equal to u times v minus integral v du. And so if you work all this out, I'll let you guys do it, but if you work all this out, you get t e to the t minus e to the t. All right, and then plus c3. And for this one, our initial condition is also 1. They're not always the same, right? It's because of our initial position here. So in this case, z of 0 should be 1. But z of 0 for this function is 0 e to the 0 minus e to the 0 plus c3, right, which is negative 1 plus c3, and that's supposed to equal positive 1. And so just solving this tells us c3 has to be 2. And so our z component of our position function is going to be t e to the t minus e to the t plus 2. All right, and so our final answer is that the position function of the particle is given by this vector function, right? R of t is equal to this very specific function, no unknowns on this one. So 1/2 t squared plus 1 e to the t in the second component, and then t e to the t minus e to the t plus 2. All right, and so that's our final answer. All right, so this lecture was mostly just an introduction to derivatives and integrals of these vector functions, and in the next lecture we'll start using them to learn more information about the space curves associated with the vector functions. So I'll see you in the next one.